Okay, should I go ahead?
Yes.
Okay, so hi everyone. So I am Sebastiano Bernuzzi from University of Jena in Germany, and well, I want to thank you very much for the opportunity of speaking at the TCAN meeting. And the subject of my talk is a popular one in this meeting. It's about binary neutron star mergers. And in particular, I want to discuss well, what we have from current simulations, numerical relativity simulations and model, and what we have to do, what we will want for the next observations. Okay. So let me start from what we have, and let me start from actually an application, in particular on the the constraints on the mass-reduced diagram after 1708-17. This is work by Matteo Breschi, who's a PhD student here at Jena. And while we have seen this kind of plots, what we have done here was to start from a prior 90% confidence level, which is this gray area, minimal assumptions, so general activity, causality, minimum, maximum mass of the TOV, and we have added constraints from gravitational wave observation, the kilonova associated to that, and also nicer. And if you do that, the prior shrinks a bit, and you can actually constrain a bit more the radius of the 1.4 solar masses neutron star. So different groups have done this type of analysis with different models, with different data. Those that use this kind of data have actually very, very similar result, although they have used perhaps very different model. And this matches with the discussion of Andrew yesterday, that basically suggested that we are basically prior dominated, not in the sense that these observations are uninformative, but in the sense that we are not yet at high precision measurement for this type of analysis. There are many contributions from numerical relativity models into this analysis, and this is what I want to discuss next. And in particular, waiting for new data, new observation, we have to develop them such that, okay, so it's blocked. I don't know why this does this, but well, we have to keep on developing these things so to be ready for actual high precision measurement of this type. So this is a cartoon that you have seen many times in these days, and this is a list on the right of contribution that all come from 3+1 numerical relativity simulation. So of course, waveforms with a focus on tidal effects up to merger. For the future, there will be also post-merger signals to be detected. There's a contribution from numerical relativity regarding the remnants, so whatever the merger is producing. It's a unique information that the simulation can give us. And of course, the contribution from and models from for the kilonova, which are directly connected to modeling the outflows with different type of outflows, different time scales. Okay, so I'll try to touch hopefully all of this topic and explain a bit the contribution of Jena and other members of the core collaborations. So let me start from the inference of the gravitational wave, and here we focus on tides. So here the difficulty is that, as it is well known since long time, tides are essentially measured at very, very, very high frequency. And that's where systematics and high velocities, strong field high velocity, are more important. So it's not really a place where a numerical relativity can inform us about, in some sense, the exact solution. And in this work that was done by Rosella Gamba, another PhD student here at Jena, we study quite in detail systematics between among the current gravitational wave models. And systematic do exist and are very well understood in some sense, and are very clear to gravitational wave modelers. But for the particular event, of course, these were not the dominating effect. However, you can still see that they are present. And for example, here in the right plot, you see that the posterior for the reduced tidal parameter, depending on the analysis choice and on the models that you use, can shift and can have double peaks and so on and so forth. So starting from what we know of the theoretical model, what we did and what we concluded in this work is that the way to mitigate this systematic effect that are present already in 1817 is simply to cut the analysis at 1 kilohertz. And if you do that, essentially you get larger posterior, you get larger uncertainty, slightly larger, actually not much. But you do get a substantial agreement between essentially all the possible templates that you can throw at it. The byproduct of that is that also the posterior shifts and on the right, and so you get an estimate of the radius which is slightly larger than early estimate. So other groups have reach the conclusion of cutting this analysis at 1 kilohertz, maybe through other route, other consideration, but essentially this suggests that a combination of noise detector glitches and waveform systematic point to robust analysis that should be cut at 1 kilohertz. Systematics. So we told about systematics, and these are the systematics. So the right plot here shows the relative bias of this tidal parameter with respect to the statistical bias as a function of the SNR and for different for the different waveform models. And what you see is that, of course, a low SNR, this doesn't count much, but as you start to reach SNR order 100, essentially you get systematically you get dominated by systematics. Okay, so this in practice means that if tomorrow we have a very loud event, our results on the tidal parameter could not be trusted. And perhaps being a bit more conservative, this means that for 3G and Einstein telescope and Cosmic Explorer, if the model don't develop, we will be fully systematics dominated. So what can numerical relativity do here? And what is the status of numerical relativity? So some of the status is summarized in the table on the right, which calculate faithfulnesses. It's a measure of the precision, the intrinsic precision of the numerical relativity calculation among different between the different resolutions. Okay? And the message of this complicated table is that if the SNR remain sufficiently small, say threshold detection or up to 15, then numerical relativity is fine. But of course, you cannot measure very well the tidal parameters. On the other hand, when SNR increases and the measurement of the tidal parameter becomes more precise and, of course, larger scientific impact, the crosses means that the model are not good enough. So what we have done so far to improve the situation or arrive to this situation, well, there are a bunch of technical things that have technical development that have been done over the year. I just want to summarize them. So some groups use high order finite difference schemes for hydrodynamics, which are, in my opinion, absolutely necessary to calculate waveform. We develop eccentricity controlled initial data, and we have also performed some good comparison. So overall, the situation is not too bad in the sense that some waveforms are convergent, comparisons would find that there's agreement among different codes with different choices within the error bars, of course. But still, as I showed before, these error bars are still too large for very high SNRs, or if you want to improve the current waveform model, like effective one-body models, for example. So this is more recent work on this line, and here's my technical 2 slides. What we have tried to do here to improve the situation was to implement a scheme that is we call entropy flux limiter scheme, which is very simple actually. In the numerical flux of the conservation law that represents general relativistic hydrodynamics, what we do is simply interpolate between the a centered unlimited scheme of high order and your standard finite volume scheme of your choice. And the interpolation is based on the physical entropy. Okay, so as you see here in this picture on top, on the left there is the entropy, on the right just the density. The entropy is larger, of course, at the surface of the stars or during the collision interface of the 2 stars, or, for example, in the expanded shocks after mergers. Okay, so what this scheme does is to deposit the numerical dissipation only exclusively where there are these narrow yellow regions, and everywhere else it's an unimportant scheme. So from this plot, you see that, for example, when the stars are in spirally, the entropy is only large at the surface, and the main plot in the center is just a very rapidly rotating single star, and this is the velocity profile. And on top, I compare the velocity along x of the new scheme with the exact solution. It's an equilibrium solution, and other scheme, and you see that the radius is the surface is not very well captured. And on the bottom, I show that not only the scheme captures the profile and the surface, but it is also convergent, and it is convergent to the exact solution. So this was very nice for orbiting star, and as the panel on the small panel on the right in the back shows, it also captures the collisional shock and the expansion of the spiral arms during mergers. Does it do good for the waveforms? The answer is yes. This is a plot, again, a mismatch between different resolution. The blue is the same simulation with the older high order scheme, and the red is the new scheme, and n is of course the resolution, and so you see that the mismatch gets smaller and smaller and converges rather fast and improves resolution. And the bottom line is that at the moment with the schemes, it seems possible with affordable resolution up to 200 cube points resolving the star, which is still very large but affordable. We can meet here the accuracy criterion for an SNR approximately 80. So there's more work to do, but I think this is promising. So to look a bit more in the future, again on the side of gravitational wave, we do have prediction for the complete spectrum, which is you see shown here. And the way that we do have model that covers the entire spectrum, predicts the entire spectrum, and it can be used within Bayesian inference. And the idea is, of course, to attach spiral merger model, like, for example, advanced effective one-body models, to analytical models that are based on numerical relativity. And the way that the numerical relativity information is included is through equation state independent or equation state insensitive relation among the different features of the different quantity of the spectrum, and of course the parameters of the polymer. So can we detect post-merger with these models? The answer is if they exist and if the prediction are correct, yes. But we will need very high SMR. And so we will need to think about 3G. Okay, so there is just estimate that suggests that to be detected with standard match filtering analysis, you would need SNR in the kilohertz regime, in the post-merger regime of about 8, and this means a very, very high SNR for the spiral merger frequencies. And then, assuming that we detect this, what can we do with that? The first question was, okay, what's the new information that detecting a complete signal can bring us with respect to just detecting the inspiral merger? And remember that the inspiral merger in these cases will be very, very informative and will be very high SNR. So one possible answer to this question is given by the plot on the left. This is one of these equation of state insensitive relation that we empirically found from the numerical relativity simulation, and that shows that there's a correlation between the maximum density in the QV diagram and the equilibrium diagram and the peak frequency of the spectrum. And so you can ask, okay, I run a spiral merger analysis, and then I run a full analysis. What do I learn? And the answer is on the right. The gray is the usual prior, 90% confidence. And so we pick, this is an injection, so it's a mock analysis. We pick an equation of state that is this black line that is actually outside the 90% confidence region of the prior in some high density part. And what you can see is that the red, the spiral merger analysis with the T at the minimum SNR threshold for detecting post-merger actually is very informative, right? It's a strong constraint, especially around the masses of the individual stars, so around 1.4. However, and so you can reconstruct and constrain the entire mass ratio, almost the entire mass ratios diagram, but it's out here at very high density. If you include also the kilohertz, the post-merger spectrum, what you find is that you have a correct prediction of the injected signal. This means that you can, with this approach, you can constrain the maximum mass to 15% and also the maximum density. The model itself is built not on the previous relations, but on this relation that correlates, again, the peak frequency with actually that other parameter. This is kappa is something that is conceptually equivalent to lambda tilde, and it's a quite tight relation that has been designed with a large number of numerical relativity simulation. So one of the questions that is around and that was around since long time is, okay, how about the equation of state is a softening at very, very high density, for instance, due to degrees of freedom, hyperons, quark confinement transitions, so things like that. And can we detect this softening with a combined detection of inspiral and post-merger? And we did several of these experiments. Here we focus on a particular equation of state and a particular simulation. They don't really matter, but they're with hyperons. And you see the wavefronts here for two different masses. At sufficiently low mass, they don't differ at all. But there is a sweet spot, sufficiently high mass, in which you get a remnant that is significantly more compact, that collapse much earlier, and significantly differ from the remnant that is described by an equation of state that is purely hadronic. So this is the Bayesian analysis of the two cases. And as you see, few parameters, in this case, the time of collapse, but could be also the frequency, the peak frequency or other parameter. You could see that the posterior start to deviate, and you could say in principle that yes, a deviation of the quasi-universal relation indicates the presence of softening mechanism in the matter. Is this an accurate statement? I don't think so. There are several caveats to that. The first caveat is that this happens, first of all, for a very small windows of parameter, which are equation of state dependent. So you have to be very lucky. The second caveat is technical. The equation of state on quasi-universal relation have their own theoretical uncertainty. They have their own scatter, as you see from this residual. So what we did to address this was to introduce in the analysis recalibration parameters that precisely take into account in the Bayesian analysis the fact that there is an uncertainty in the model. And here they are critical because they can tell you, how many sigma you are out. From how many sigma is the violation from the given model, which in this case is the quasi-universal relation. And also another aspect is that it's really a morphology, it's really a difference in the morphology of the waves. So it can be captured, it is not necessarily captured by a single parameter, but is more, it's more a global thing due to the morphology. And of course, the best that you can do with this approach, since you don't know the theoretical equation of state, is only to say that, yes, we detected a deviation from our model, which is the quasi-universal relation. But jumping from that, from there to say, okay, there's been a quark phase transition, it's risky. So, and this is an example. Since you infer the deviation of the specific model, it is the significance of that it is as good as your model. And this is just an example that shows with the same data, two different ways of designing equation of state independent relation between the peak frequency and this particular radius. And as you see, there is a significant scatter in one case, where there is in the other. Okay. Now going towards remnant and closing the gravitational wave here. Remnants are also important, especially for astrophysics to interpret counterpart. And this is an example how the gravitational wave analysis, actually of the inspirer alone, together with numerical relativity information, can help the interpretation of the counterpart. Here, the threshold mass for the collapse, for the prompt collapse of the remnant, is inferred from the gravitational wave data, again using quasi-universal relation that are inferred from numerical relativity. And in the case of 17817, this approach essentially quantitatively support the idea that the remnant has to be short-lived, as also inferred from astrophysical arguments. Of course, for the other, and in particular, we calculated the probability of prompt collapse, subject to, of course, the pulsar maximum, the pulsar constraint of the maximum mass, is actually less than 10%. Okay, so this is a quantitative way, if you want, of supporting the interpretation of the counterpart. And in the case of the other binary, of course, we find it's a high mass. We find a high probability for prompt collapse. So as I mentioned, this analysis has been done with universal relation connecting some maximum TUV mass to the property of the binary. I think David has explained this in much detail in his talk, so I will simply skip it. But I will mention that these relations are reasonably robust, as you see from this plot, for equal mass case. For an equal mass case, as you may expect, there's an interesting phenomenon. The companion actually disrupts almost completely during merger. And because the primary is very massive, the accretion immediately triggers black hole formation. So this is a prompt collapse, but with very different phenomenologies due to the accretion of the disrupted secondary object. And the interesting part and the interesting bit, the byproduct of that is that you get a very, very massive disk around the newly formed black hole. In this case, characterizing quantitatively the prompt collapse is much harder. I must say it is the mass ratio effect is a subdominant effect with respect to the maximum mass criterion. But if you factorize out, as we have done here, the behavior of the threshold mass for unequal masses, and you plot the rest, you see that there's a very clear trend as a function of the mass ratio, and particularly the threshold for prompt collapse lowers, and it is also equation of state dependent. And Albino Perego has thought very hard about it. Immediately was a bit puzzling to find an order in this type of data. But then he came out with a very interesting observation. This behavior here directly correlates with the nuclear incompressibility of nuclear matter at the maximum density. So in other terms, this threshold here as a function of Q correlate with the points here in the nuclear physics diagram and have the correct order that you can find in this point. So higher incompressibility means here a lower threshold. I think this is very interesting. It matches with the idea that the dynamics in this case is dominated by, how much the matter disrupt, compress, and also opens for some application in the future to estimate this parameter, which is not well constrained as far as I understand by any other experiment. And here my numerical comment or technical comment. There's much to do on this side. And for example, if you compare our data with data that are calculated, which are calculated numerical activity with the mesh-based code, if you compare to other published result that use conformally flat approximation of gravity and SPH, there's a substantial disagreement for several data sets. Okay, so this remains something to explore further. And staying with the remnants, this I think is my slide about the remnant. One open question that has been discussed in several talks this week is the following. Assume that there's no prompt collapse, assume that you have sufficiently massive neutron star remnant. What we find from our simulation is that all these, this is just one example on the right, but actually, if you check this paper, there's an entire set of simulation that prove this. What you find is that all these neutron star remnants are born with an excess of angular momentum. So we call them super Keplerian. If you plot them in a baryon mass versus angular momentum diagram, and you included the diagram, the region, the gray region here of rotating star equilibrium, they all stay on the right of this region. And of course, they are massive, so they stay above. So these are neutron star object that would be called hypermassive neutron stars, according to the equilibrium configuration, characterization for the same baryon mass. But this doesn't mean at all that they will collapse to black hole. In fact, what could happen, and this is an extrapolation of the numerical relativity result, that on a circular timescale, they could actually shed maybe 20–40% of the mass in the outer regions, such that they actually arrive to be a highly spinning, to enter the equilibrium region and actually be stable, rapidly rotating neutron star. So this requires to consider the long-term evolution, and because gravitational waves are efficiently emitted and the timescale gets longer and longer, the evolution on this timescale will be mainly dominated and governed by neutrino cooling and viscous processes. So neutrino cooling is the main mechanism to cool the thing, and so it tends to contract the remnant. Viscous process, of course, do the opposite. Okay, so this means that one has to simulate very in much detail all these effects, and in order to obtain an actual quantitative prediction. Because if you have too much cooling or too much viscosity, then you evolve in the other direction. Okay, and the idea is that in this process, if the outer part of the remnant are sufficiently are expanding, sufficiently outwards, then you can have nuclear combination of particle, and this creates the massive winds, which are triggered by various viscous processes. Could be neutrino, could be MHD, but of course is the big catch, immediate catch for the groups that are working on this aspect. So let me now go to the other part of the analysis of the first slide. That is the inference on the actual kilonova data. Sorry. So the kilonova can actually inform us also on the tidal polarizability parameters and the mass ratio, essentially from the color of the kilonova, from which you can infer the presence of the disk and the amount of mass. So this was pointed out already some time ago now. And what we have done is to use numerical relativity informed but semi-analytic kilonova models from Albino Perego and perform model selection on the observations. Particularly, we have considered different models, one component, two components, say dynamical ejector and winds, three component, winds with different opacity, and we have considered spherical models and anisotropic model, all these sort of combinations. And what the data suggests is that the favored model is actually a three-component model with geometrical dependence, so at least anisotropic type of source of emission. And this is interesting because we have also simulated, I think it's 100 simulation targeted to the event. And we have calculated, of course, dynamical ejecta and early winds. So these are simulations that can span up to 100 milliseconds. And these are the result. So this is the ejecta mass and the average velocity, and the ejecta mass and the electron fraction. All the simulation have, of course, the general relativity, but also neutrino cooling with leakage scheme, neutrino absorption with M0 scheme, and the subgrid model for MHD-induced turbulent viscosity. And so these plots show the different results. So the estimate from the simulation, from the different simulation, all targeted. And whereas the boxes are the two-component spherical fitting model that is popularly used to describe the observation. So the red, the model of the story of the red of the blue. And as you see here, there are points for the dynamical ejecta. There are points that include also the early wind, and there are upper limits, of course, for this wind. The simulation at some point stopped. Well, what you can see is that none of the points is actually inside the boxes. Okay, so this means that well, we know this from numerical relativity that well, there are more than two components. And it also means that it's not obvious to interpret the blue and the red as coming from, say, just the dynamical ejecta or the wind. So the reality is most likely much more complicated, okay? And the fit cannot be interpreted in a simple way. So one key, again, my technical comment, one key aspect in this simulation is the proper simulation of weak interaction. I think a few years ago, this came a bit as a surprise for some of us, but it's fine. And what you see here is an example of it. On the right, you see a simulation with cooling and absorptions of neutrino. On the left, you see the same simulation with cooling only. The upper panel is the mass fractions, the amount of mass in a given bin of the polar angle. And the bottom panel shows the electron fraction, histogram of the electron fraction. And you see that especially here above the remnant, the ejecta is very different in the two cases. Absorption gives you more mass in those regions, and in those regions the electron fraction is also much higher. Okay, so already for the dynamical ejecta, it's necessary to include neutrino thing, and this change both kinematical properties and the composition. And this just stresses the same fact. So we collected from ours and from literature almost all the results available. And the color here represented the, so again, it's mass and average velocity. And the different color in the plot represents data from simulation that are done with leakage only, the green, and with some scheme that can take into account neutrino heating, and the gray are just polygons. So there's no neutrino microphysics at all. Okay. And you see visually already that typically leakage gives you less masses. Polytropes are spread all over, and so on and so forth. So to try to improve the situation, we, together with Radice, we move to an improved neutrino transport scheme. So based on the, it's gray, but it's based on the truncated momenta, is much more consistent. It's supposed to actually simulate properly fixed sources and can also take into account out of equilibrium effects. And these are snapshots that shows again comparison between leakage plus M0 and the M1 simulation. And what you see is the electron fraction. And you see that the polar region above the remnant, which is this small dot here, magenta, has much higher electron fraction, but also the composition is also different in the disk and in the equatorial region. So there are qualitatively analogies, but there are also quantitative difference, which of course matter the moment that you want to properly model a kilonova. And this is a short summary of the result. So we do find with the scheme trapped neutrino gas in the remnant. Interestingly, on the equatorial equatorial latitudes, the neutrino from the remnant are actually shielded, but then it's the disk that radiates the material that is outside. So there's a variation in electron fraction that is geometrically dependent, and it is due to different processes. We also found, in general, the M1 scheme gives lower luminosity than the neutrino luminosity than the M0 scheme. And we also started to look at out of equilibrium effect and found no evidence so far. On the technical side, there are very few schemes of this type and applied to the major problem. And we essentially follow the Gray plus scheme of François Foucault. But with respect to the prescription there, that essentially comes from Luke Roberts and Evan O'Connor, there are a few important differences. One is that the numerical fluxes are actually calculated correctly in the diffusion limit. and we don't use any ad hoc prescription for the limit imposing the relativistic equations. Another aspect is that we use complete sources in the M1. So with all the Doppler terms, and this is actually important also in simple tests, as you see in this plot. If you approximate the sources, green and black are two different approximation, you don't get the right solution, which is the reference correct. I don't know how long I still have, or if I'm done.
Well, another minute or two. You know, you have started 3 to 5 minutes late, so.
Okay, I have just two slides, and I can go very quickly. So as I mentioned at the beginning, of course, we are looking forward. We are preparing high precision, quantitatively detailed simulations. And if you want to start, to resolve all these effects, neutrinos, MHD, turbulence, and so on, we realized that we need different infrastructure than what is available. So both in Jena and Penn State and elsewhere, other members of the core collaboration, we are developing this code that is based on the Athena++ code of GSTO in Princeton. And of course, we have not really rebranded because it's just a branch of it. And we'll also release together with Athena++, but we rebranded GR because, of course, what it adds is, for the moment, the dynamical space-time. This is an interesting code because it's very well designed for heavy parallel calculations. And what we have done, beside adding the general relativity module, was also to rewrite or to extend the AMR using vertex center, a vertex center approach, which can be useful for metric evolution in certain application. And the code at the moment works beautifully with full binary black hole simulation. This is just an example on the bottom right. And the main panel is of course the highlight. It scales very well up to all the processor we could throw it. So it's about 10 to the 4 CPUs, and it has almost perfect weak scaling and also optimal strong scaling, given of course the sufficient resolution to fit the entire PDs in memory. So this is, as I mentioned, effort of Boris Tatsuta, who's a postdoc here at Jena, Will Cook, also postdoc here in Jena, and David Radice and his group. Very quickly, we have done the first neutron star application with Athena, and we have reinvestigated the open problem of magnetic fields in isolated neutron star. So it is well known that if you start with a poloidal field, this is not a stable equilibrium. So the poloidal field evolves. There are various understood MHD instability that immediately develops, and typically you get the development of the toroidal component. But it's unclear if this it's still unclear if this type of configuration that emerged dynamically from the 3D simulation actually is a stable equilibrium, is a quasi-stable equilibrium, and so on and so forth. So we try to revisit this problem, and what we found is that, well, we were able to run simulation at higher resolution than previously done, and way much longer. And what we found is that initially the toroidal component, if you start from 0, of course, gets energy in the channel and increases, and it can increase up to 20% of the initial poloidal energy at about 12 Alphen time. But later, and here is the region which was not previously simulated, we find that the energy decays again. And this is shown here in the different contribution to the total energy. And the magnetic energy, which is the red, does reach a sort of equilibrium. And it was suggested that some of the long-term evolution could be could be dominated by turbulence at small scales. So in this simulation, we don't find that. Actually, the magnetic energy seems to be dissipated via into heat. It's heating the star. And we don't find any evidence, at least at this resolution, for turbulent phenomena. However, these are not yet enough as a resolution. So there's a resolution dependency in the of the heat that is dissipated, and there's also an issue with the boundary. So in some sense, we did step beyond, but there's still much to learn. And this is relevant also for mergers, of course, because most of the simulation, as far as I know, are initialized with the poloidal field, which of course most likely cannot exist in physics, as far as I understand. Okay, I'm trying to switch I'm done. The next slide, I have the conclusion. Okay, here are my conclusion. I think if I'm out of time, I simply skip them. I think the take-home message is common to a few other talks. I just wanted to advertise that we do a position at Jena. So if you want to work with us, feel free to contact me. And thank you for listening.
Okay, thank you very much for an interesting talk. And I'd also like to apologize, particularly to Sebastiano, but also to the audience, that a computer glitch just as Sebastiano began his talk prevented me from giving him a proper introduction at the beginning.
No problem, of course.
Let's see, please raise your hands if I can ask a question. All right. Looks like Svi was first to raise his hand. Go ahead.
Hi, thank you for this very nice talk. I have a question on this issue of the kilonova, which is calculated. On one hand, you said that you can produce the kilonova, and you will even argue that there is some conclusions from the fits to the kilonova in one slide. But then in the next slide, you sort of showed that in all the simulations, there is not enough fast material to produce the blue kilonova. So I see sort of a contradiction between between these two slides. So can you explain to me what is going on, please?
Yeah, I'm not sure what slide you are referring. Maybe I try to put them back.
No, in one of the slides you were showing how you infer that the kilonova must have three components, and one of the previous slides.
Okay, I see. I got it. Is this one,
then
right?
You say so this means, yeah, this means that you managed to fit the kilonova to your simulation. Then I look at the next slide, and if you go to the next slide, please, 23, we see this figure on the left, and for the blue kilonova, we need fast material at around 0.25 C, maybe slightly more, maybe slightly less, and none of the simulation produces it. So,
yeah, but this analysis
22. How is 22 consistent with 23?
Yeah, but this analysis is not done with this analysis is not done with numerical relativity. I don't think there's any contradiction. So this analysis is done with the numerical relativity informed semi-analytical kilonova model, but we let the masses and the velocity to vary freely, and we infer the masses.
Oh, okay.
Whereas here, of course, we are plotting just the masses and the velocity.
Okay. That's very clear. So this brings us sort of back to the problem which was raised in one of the earlier talks, that the simulation do not produce enough fast material.
The nice part of this work on the inference is that the inferred mass and velocity from the inference are at least ballpark in the right spot. They are comparable to the simulation. But of course, what we cannot control is the amount of disk mass, because that we don't have from direct simulation. We don't have it complete. We have only lower limits. And of course, there's the entire issue of the opacity that we infer that, well, as you can guess from this cartoon, they are just average gray effective opacity, just parameters, right? And this we cannot compare with anything. The actual light curve is an analytical model. So.
No, the point is that regardless of the opacity, to produce the the initial fast component, initial bright component, you have to have material moving with very high velocity in order that it will become optically thin sufficiently early. And this material is, and a lot of it to produce this signal. So this is the problem that I just wanted to be sure that there is no contradiction in between what I understand about the problem and your presentation. And my bottom line understanding is that there is no contradiction. You agree that you need a lot of fast material, and you agree
yes.
that the current simulation do not produce it.
Yes.
Okay.
Well, I think in the result there's no contradiction, but that doesn't mean that we have understood everything.
Okay. Vasily has been waiting to ask his question. Go ahead.
Hello, very nice talk. I have a question about the entropy limiting for the fluxes. So are you using central stencils on the characteristic fields where you're allowed to for the entropy, and then in the rest you do normal upwinding in the primitives with higher order reconstruction? Is that what you're doing?
Yes, precisely.
So what is it that saves you then in the entropy case? Is it the central stencil, or is it the reconstruction in the characteristic fields? Because if you use Wiener in the final volume, then I mean Wiener in the smooth regions should also select the stencil that is as non-dissipative as possible, right?
No, that does not happen.
Okay.
So it does not happen. So we actually use, so this is always with characteristic decomposition for both fluxes. So we have a high order and a low order flux. Both of them are constructed with characteristic decomposition, but the high order is with an unlimited scheme of the order that you prefer, but it's an unlimited scheme. In this case, if it is fifth order, but you can have it of arbitrary order. The low order, it's not really a low order flux, but it's actually our old high order Wiener scheme. But you can use also there. You can use a finite volume. You can use a Godunov method. Actually, for some shock tubes, we have coupled it to a finite volume and Godunov. We have coupled from Godunov method on the characteristic fields. So the choice is completely arbitrary. And what I think it's not true, because of a paper on that, is that we know Z can select the stencil. So in the if you take a single star profile and plot the Wiener weights on the single star profile, you see that the weights are not optimal. And so even if the solution is probably sufficiently smooth, that a high order scheme can be applied without oscillation, the Wiener does not, and I've tested 2 or 3 of them. The Wiener does not that does not gives you the optimal weights that you would expect for full fifth order convergence. So that's why we try to extend a bit the method and actually try to use an unlimited scheme.
Okay, and then but you're still upwinding, I presume, right, for stability?
So it is the high order is let's say Wiener unlimited, and the low order here is not really low order, is a Wiener scheme with characteristic decomposition. The final difference is the standard conservative final difference between fluxes of the interfaces.
Okay. Okay.
Are there any more questions?
Thank you.
All right. I guess